A few weeks ago, I attended the 16th Biennial History of Astronomy workshop at University of Notre Dame. While this conference isn't strictly limited to pre-telescopic astronomy, there were several talks that were relevant to this topic. Additionally, we took a field trip to the Adler Planetarium in Chicago and got a behind-the-scenes look at some of their special collections. So, stay tuned to find out what they had to say about astronomy before the telescope. First things first. This conference is held every 2 years in June at the University of Notre Dame in South Bend, Indiana. The theme for this year's conference was Visual Practices in the Production and Transmission of Astronomical Knowledge. As with most conferences, presentations are not strictly limited to this topic, but it does give a focus for things to proceed along, and I generally think it's helpful because it helps get everyone thinking in the same direction, which can help spark synergies. And lastly, before diving in, I want to apologize if I don't state things quite correctly. Without having a paper to digest at my own leisure, I'm relying entirely on my notes and my memory here, so I may occasionally misstate things as I'm trying to fill in the gaps. The first talk of the event was the keynote speaker, Dr. Matteo Valeriani, who was speaking on the knowledge economy of the geocentric astronomy from the 13th to 17th centuries. This talk stemmed from Dr. Valeriani's work at the Max Planck Institute for the History of Science in Berlin. Specifically, this project began with looking at a single text, De Sphera by Johann de Sacrobosco. This text is essentially a primer for understanding the celestial sphere. Originally written in the early 13th century, this book was wildly successful and continued to be reprinted over and over again all the way to the 17th century. Dr. Valeriani and his team looked at as many editions of this text as they could find to see how the knowledge surrounding it evolved. To explain, De Sphera is a pretty short text, easily readable in an afternoon. So, quite often, it was bound with commentaries, annotations, or other related texts. For example, here's my 1608 copy of De Sphera. It begins with a preface and annotations from Jacob Martini before presenting the actual text of De Sphera. The text is then followed by a scholia by Eli Veneto, and another commentary by Pedro Nunes, a portion of the Elements of Astronomy by Alfagrani, a compendium on the sphere by Piero Valeriano, and a short text on eclipses by Proculus. In short, Dr. Valeriani's team was trying to examine how the corpus surrounding De Sphera evolved over time. So they cataloged every edition of this text that they could find to examine what texts it was packaged with, who printed it, where, and when. Not only did they examine the text, but they were also interested in the images printed with the texts, as well as what tables were included. This required AI to help them speedily compare the tens of thousands of pages of images they acquired. The project also expanded to several other texts related to fundamental spherical astronomy. What the team discovered is that the texts became standardized, with important editions essentially taking over the market. For example, in 1531, a printing entitled Liber Johannes de Sacrobusto de Sphera, printed in Wittenberg, included a letter from Philip Melanchthon to one Simon Grynaeus, encouraging the studying of astronomy. His argument was religious, as understanding astronomy would help students of religion untangle chronologies, as many historic events were described by their contemporaries in astronomical contexts. Effectively, as time went on, we started seeing these books all containing more or less the same set of texts, leading to a standardization of knowledge growing throughout the 16th century. If you'd like to read more about this research, I've put some links in the description. The second talk that pertained to pre-telescopic astronomy was from PhD student Erica Mazeros at Brown University, who discussed an odd way a particular number was used in Babylonian mathematical astronomy. Although I've discussed Babylonian constellations on this channel, I haven't discussed their mathematical astronomy all that much, so let's start with a quick overview. As we know, planets don't move across the sky in a consistent manner. They speed up, slow down, and reverse direction. Ptolemy models this with the various bodies rotating on circles, which is essentially modeling this deviation from the average speed with a sine function. However, the Babylonian astronomers weren't quite so advanced and relied on cruder methods. In general, historians identify two models for the Babylonian mathematics called System A and System B. System A is essentially a step function in which the planet moves at a fast speed for parts of its motion and a slower speed for another part, constant in both areas with no in-between. System B is slightly more advanced using a zigzag function, closer to a sine curve, but not quite there. For the Sun and Moon, this also becomes inherently intertwined with an approximately 18-year cycle of eclipses known as the Saros cycle. To help manage all of this, Babylonian astronomers, much like later astronomers, created tables to assist in computation. However, historians of astronomy had trouble determining the intent behind one of the columns, which they called phi. It was eventually realized that this mysterious column was related to the variation in length of the Saros cycle. What Mazaros argued in this talk is that the way this value is discussed in the text is unusual. Specifically, when referring to the values in this columns, Babylonian astronomers did not give it a name. For example, if we wanted to discuss the value that the Sun deviated from its mean position, we would call this the anomaly in Ptolemaic astronomy, with the understanding that anomaly means a number. We're essentially using a word to mean the number yet to be determined. It's being used as a variable in sentence form. However, the Babylonian astronomers didn't do that for this value. Rather, they just referred to it by a number, in sexagesimal 21320, even in instances where the value being used wasn't actually 21320. If I understood her talk correctly, this was the theoretical maximum for the value, so this wasn't exactly pulled out of nowhere, but it's still an interesting linguistic choice. Again, more reading on this topic in the description. Next, we had a talk by Betsy Price from York University regarding the lunar model of Albertus Magnus from the 13th century as expressed in his De Natura Boni. In particular, Price argues that his work was based on two other 4th and 5th century astronomers, Martianus Capella, who wrote The Marriage of Philology and Mercury, and Ambrosius Theodosius, better known as Macrobius, who wrote a commentary on Cicero's Dream of Scipio. What Price noted is that Martianus's discussion surrounding the size of the moon is not good. At best, it's poorly explained, and at worst, it just doesn't make sense. So how then did Magnus make any sense of it? Price notes that many of the texts included diagrams that she suggests help save the argument, and that this is most likely what Magnus relied on. As a further source, it appears that Magnus also made use of the 11th century Toledan tables, which happened to be the subject of the next talk by Johanna Garzon from Brown University, who discussed a fragment of these tables in the collection at that university. The piece in question was donated to the university anonymously. As was all too often the case, the original work had been pulled apart and the vellum it was written on reused for other purposes, in this case as a book cover. Fortunately, it had not been scraped clean, so was still largely legible and was identified as a portion of the Toledo tables by Otto Neubauer. Garzon indicated that the dating of this fragment was difficult due to a lack of Spanish manuscripts from this era to compare against. While the hand in the surviving table is pretty standard, there were a few characters that were especially unusual. In particular, the numeral 2 often looks more like a Z, but in this manuscript did have more of a rounded top similar to a modern 2. We return to the subject of Sacrobosco's De Sphera in a talk by Dr. James Brannan, a former computer scientist turned historian of astronomy. In his talk, he discussed 4 times that Sacrobosco's De Sphera was translated into English, 2 from the pre-telescopic period and 2 from the 20th century. Given the previously mentioned popularity of this work and how many other languages it was translated into, what Dr. Brannan noted was unusual is that the 2 English translations done in the pre-telescopic era were both only ever done as manuscripts. De Sphera never transferred into a printed publication until Lynn Thorndike published his translation in 1949. The first known translation was done by Anthony Ashcombe in 1527 and is now in the collection at Yale. There are several notable things about this piece. It was written by at least 3 different scribes and has lots of large, colored diagrams. As such, Dr. Brannon suggests it was meant as a presentation piece, perhaps as a gift for a patron. Tracing the language used, Brannon determined it was based on a Latin version of De Sphera printed in 1521. It is unclear why, after all the work that Ashcombe went through to author this translation, he did not seek to have it printed, given that he lived until at least the 1550s. The second translation was authored in 1550 by William Thomas, who served in the court of Count Edward VI. Dr. Brannon tracked the basis of Thomas's translation to a 1545 Latin edition. This manuscript had hand-drawn versions of the printed diagrams, which helped identify its source. It is now in the collection of Egerton University. As for why this work never made it to print, it may have had something to do with the fact that Thomas got swept up in Wyatt's rebellion in 1554, leading to his execution. We then had a talk from Molly Lamaukas, who recently completed her master's at the University of Chicago and wrote her thesis on the usage of volvelles, rotating paper discs that could be used to illustrate concepts or perform analog calculations. The epitome of this art came in 1540 in Peter Apian's work Astronomicum Caesarium. Lamaukas states that there is a popular conception in which volvelles fell out of fashion due to them being largely used to teach geocentrism, and Copernicus's heliocentric model being released 3 years later in 1543. Lamaukas argued that the declining popularity of geocentrism was not the cause of the decline in the volvelle. Rather, she argues that volvelles were simply not useful enough to justify their continued production. I think Lamaukas is entirely correct in her claim, although I've never heard the underlying assumption that she's attempting to disprove. However, assuming that it is a common belief, I'd offer a few arguments against it. First off, I'm not confident in the association of volvelles and geocentrism. As Lamaukas points out, volvelles were not necessarily tied to a geocentric cosmology. An example that I would give is a book on the art of navigation, originally written by Martin Cortez in 1545 and translated into English by Richard Eden later that century. This book featured several volvelles used for telling time or computing corrections for the North Celestial Pole based on observations of Polaris, since Polaris is not directly at the pole. In other words, volvelles were also useful for teaching celestial navigation, which is not reliant on Ptolemaic geocentrism. Second, I'd be curious to track the supposed decline of the volvelle. The art of navigation continued to be printed well into the 17th century, and the aforementioned editions of Sacrobosco's De Sphera contained volvelles as well, which also continued to be published into the 17th century. Thus, I join Lamaukas in not being convinced of the base assumption. Her talk was during the sessions at the Adler Planetarium, so during the break, the curators of special collections there brought out several items for us to check out related to the talks at this conference. This included a Few version of Sacrobosco's De Sphera, a telescope by Fraunhofer, and, most exciting to me, a copy of the previously mentioned Astronomicum Caesarium by Peter Apian. This book is generally considered the most beautiful book ever printed in astronomy, and I have to agree. The work was intended as a gift to his patron, the Holy Roman Emperor Charles V, and features a collection of volvelles. These recreate the Ptolemaic geocentric model in amazing detail, allowing the user to determine the positions of planets by physically moving the disks instead of performing the tedious calculations. It's a truly stunning work that I hope to talk more about in the future, but for now, I'll just say that getting to flip through an original was a magical experience. And, as a fun fact, there's another Astronomicum Caesarium on display at the gallery at the Adler. However, that one is a facsimile from 1969. It is extremely high quality and was limited to 750 copies, but they're so good that had I not been told the one on display was a facsimile, I wouldn't have been able to tell the difference, as it reproduces the details down to the gold leaf on the page edges. The Adler also sent us home with a swag bag containing a copy of the 2019 book Times of Our Lives Sundials of the Adler Planetarium. This is the third book released detailing items in the Adler's collection. The first two were on their collection of astrolabes, which is among the largest in the world. All of these books are amazingly detailed and give a massive amount of detail about the individual items within the collection, making them useful as a resource for those interested in studying the variety found among such instruments. The final two talks on pre-telescopic astronomy both pertain to a type of instrument known as an equatorium. These instruments are, again, analog computers to determine the positions of planets, and some of the Volvelles just discussed can be considered paper equatoria. However, versions were also made in brass. The first of the talks on this instrument was supposed to be by Mostafa Yavari from University of Tehran, but his talk was cancelled as he, understandably, did not want to enter the US given the current political climate. Instead, we skip to a talk by Michael Corey from the Dresden State Art Collection on a really interesting equatorium from sometime in the 16th century. This instrument had not been well studied, and unfortunately, during the bombing of Dresden in World War II, the instrument was heavily damaged, making further study of it difficult. However, Corey and his team examined the remaining gearing and were able to model it digitally, reconstructing the damaged parts and even inferring ones that had been destroyed by understanding the logic behind the remaining ones in order to examine the device's function. The device appeared to work by having a fixed central shaft, around which the entire instrument was turned, like a steering wheel. This central shaft had a gear which turned a series of other gears and driving the motion for each of the 5 naked-eyed planets and the moon on dials on the instrument's surface. The instrument also had 2 hands, which Corey determined point out the true and mean position of the sun. Some at the conference, myself included, had skepticism that the device would function well given that the first gear in each of the gear trains for the bodies was extremely small. I missed the exact number of teeth, but it looked like less than 10, which means that it would have had to transmit a lot of force. The tooth profiles looked more like modern profiles than the triangular ones that the scholars believe would have resulted in the Antikythera mechanism performing poorly, but the small size and large force still suggested to us that this instrument would not have performed particularly well, and indeed, many of the teeth on that central gear were broken off, indicating that someone had likely tried to force it at some point. Regardless, getting to see the reconstruction of this instrument, even digitally, was quite exciting. Overall, the conference was a ton of fun. While the talks were interesting, getting to discuss things with the speakers was the largest highlight for me. Although the next conference isn't until 2027, the conference is open to anyone interested in attending, although discounts are available to students. So, if you're interested in astronomy before the telescope, consider attending the next one. I know I'll be there. Also, I made friends with the raccoons on campus.